Today we will be discussing predictive maintenance for industrial equipment. This presentation is used for educational purposes. In this presentation, we will discuss the problem statement, opportunity validation, risk and business understanding phase, solution validation plan, ML system design, and potential risks in production. The problem statement is to develop a machine learning based solution to predict equipment failures in manufacturing plants, specifically focusing on the timely maintenance of critical machinery to minimize downtime and maintenance costs. The opportunity evaluation that we have is first clear business value, where we can significantly reduce unplanned downtime and maintenance costs by identifying potential equipment failures before they occur. Next is the feasibility of ML solution, where machine learning's algorithm can analyze historical equipment data such as sensor readings and maintenance logs to identify patterns indicative of impending failures. Lastly is the impact on stakeholders, where it benefits multiple stakeholders, including plant managers, maintenance technicians, and production teams. Under Chris DM business understanding phase, aside from problem definition, we also measure the success criteria and relevant factors. Under success criteria, we measure the outcome metrics and output metrics. Under outcome metrics, the success of the predicted maintenance solution will be evaluated based on its ability to reduce unplanned downtime and maintenance costs. Under output metrics, this will include the accuracy of equipment failure predictions measured by metrics such as precision, recall, and FI score. In relevant factors, we have historical equipment data, maintenance practices, production impact, and stakeholder engagement. Under solution validation plan, our first is to um, is the user engagement, where we engage with key stakeholders within manufacturing companies, including plant managers and production teams, to gather insights into their current maintenance practices, pain points, and expectations for predictive maintenance solution. The next one is prototype demonstration, where we develop a prototype of the predictive maintenance solution incorporating machine learning algorithms to analyze historical equipment data and predict potential failures. Under feedback collection, we collect feedback from potential users through interviews, surveys, and usability tests to assess their perceptions of the predictive maintenance solution. Iterative refinement is where we iterate on the prototype based on user feedback, incorporating suggested improvements and addressing any concerns or limitations identified during the validation process. Under pilot implementation, collaborate with a select group of manufacturing companies to pilot the predictive maintenance solution in real world settings. And lastly is the evaluation, where we evaluate the effectiveness of the predictive maintenance solution based on predefined success criteria, including its ability to accurately predict equipment failures. By executing this validation plan, we aim to ensure that the predictive maintenance solution meets the needs and expectations of potential users within manufacturing plants, ultimately validating its effectiveness and feasibility for widespread adoption. Under ML system design, we have data collection and integration, feature engineering, model selection and training, real-time prediction and alerting, integration with existing systems, scalability, and performance. By making these key system level architecture decisions, the ML system for predictive maintenance is designed to effectively analyze equipment data, generate accurate predictions of failures, and facilitate proactive maintenance actions to minimize downtime and maintenance costs. We also have potential risks in production. In production, the predictive maintenance model may encounter several potential risks and challenges, including drift concerns and other issues. For drift concerns, we have data drift and concept drift. Under data drift, can adversely affect model performance if the model is trained on outdated data that no longer accurately represents the current state of the equipment. And in under concept drift, it refers to the changes in the underlying relationships between input features and target variables over time. But under serving skew, training serving skew occurs when there are differences between the data distribution used for training the model and the data distribution encountered during production inference. The next one is latency. So under latency, this refers to the delay between the time when the data is collected from sensors and the time when predictions are generated by the model. Lastly is the model robustness and generalization, where the predictive maintenance model may lack robustness and fail to generalize well to new or unseen equipment conditions or failure modes. We reached the end of this presentation. Thank you.